Calculus, video 45, critical values, local extrema, and absolute extrema. So throughout this video and the next few videos involving extrema, absolute extrema, critical values, inflection points, concavity, and curve sketching, there's a lot of definitions, and so it may be helpful as we're going through here and I'm reading off these definitions to pause the video to give yourself time to write those definitions down. We'll start with a definition here of critical values, or sometimes referred to as critical points. Okay, and you may even see me abbreviate critical values or critical points, like critical points CP for critical point. All right, so the same idea for critical value and critical point. The value is if we're just looking for the x. The point is if we want the x and the y. Critical values are values of x such that the derivative is equal to 0 or the derivative is undefined. Critical values are values of x such that f prime of x is equal to 0 or f prime of x is undefined. What we're going to find out are that our local extrema, which are extrema here, we're talking about our local max and local min. Local max and local min. Together they are defined as the local extrema. Are critical values. So local extrema occur at critical values, but not all critical values are local extrema. All right. To help make that sentence make sense, I have a couple of graphs drawn below. I have a curve on the left here. Kind of looks like maybe an x cubed kind of a function, degree 3 polynomial. And what we're going to find out is where the critical values, remember, occur whenever the derivative is equal to 0 or the derivative is undefined. All right, that's when our critical points or critical values will occur. On the left there, we see that we will have a critical value here, a critical point here, because the slope is 0 there, therefore the derivative must be 0 there. So we will get a critical value, or critical point. I'll use the CP, critical point. At that critical point, it turns out that that is a relative maximum. A relative maximum is a point such that the y value at that point is greater than or equal to the y values of all the points nearby. So this is a critical point, and it is a relative max. This is a situation where the relative extrema, the relative max in this case, comes from a critical point. In fact, all relative extrema will come from critical points, but as we'll see in a minute, not all critical points end up being relative extrema. There's one more critical point on this curve. It's down here. Again, the slope there is 0, therefore the derivative at that value of x is equal to 0. That makes it a critical point. So it's a critical point. In this case, we find out that this is a relative min. Now here I'm using the term relative. Earlier I used the term local, right? Relative and local I'll use interchangeably. You'll see them both ways. Relative min, relative max, local min, local max, same idea. Okay, so two critical points, one being a relative max, one being a relative min. On the right graph, which looks like maybe an upside down absolute value graph, we have a point here where the derivative is undefined. Remember that when a curve comes to a sharp point like that, the derivative is undefined. That's because the slope coming from the left is not equal to the slope coming from the right. It is a critical point, and it is a relative max, or a local max. So again, the relative max coming up from a critical point, although in this case it's coming from a critical point where the derivative is undefined, versus on the left-hand side coming from a critical point where the derivative is 0. All right. Take a look, though, at the next two pictures, the next two graphs. On the left, we have a point right there, in this case it's at 0, 0, where the slope here, a different color would be helpful, the slope is actually vertical. This is the graph of the cubed root of x, and on the cubed root of x, at the point 0, 0, that slope at that point goes perfectly vertical, and then it starts to go off to the right there. So at that point, the slope is vertical. A vertical slope means that the derivative there is undefined, which makes that a critical point because the derivative is undefined. That's what makes a critical point. Derivative undefined or derivative equal to 0. However, at the point 0, 0 there, at this critical point, there is not a relative max or a relative min. Right? It is not the highest point around the neighborhood. It is not the lowest point around the neighborhood. So even though we have a critical point, we did not get a relative extrema from that critical point. No relative extrema from this critical point. And this is what we mean by all relative extrema come from critical points, but not all critical points end up being relative extrema. Some do, some don't, but all the relative extrema will come from critical points. Okay, one more example of that. On the right here we have the some version of x cubed graph, and at this point here, we see that the slope flattens out, and you get a slope of 0. F prime of x equals 0 at that point. That, by definition, makes it a critical point. Critical point again, anytime the derivative is equal to 0 or the derivative is undefined. That makes it a critical point. But once again, just like in our cubed root graph, there's no relative min or relative max at that point. It's not the highest point in the neighborhood, it's not the lowest point in the neighborhood. So once again, at this point, even though it's a critical point, no relative extrema. No relative extrema. Okay, very good. So, hopefully that makes sense. Critical values or critical points are values of x such that the derivative is equal to 0 or the derivative is undefined. And local extrema are critical values, meaning the local extrema occur at critical values, but not all critical values are local extrema. Let's take a look at the local extrema that we found a minute ago, specifically this first example. Notice what's happening around the relative max here. Right? So this point here, that's a relative max. Notice that as we approach that from the left, the curve is increasing. It's increasing here, and it is decreasing afterwards. All right? It's increasing before, it's decreasing afterwards. We're going to see later on that that's important information. When the slope is positive, a positive slope, f prime positive means the slope is increasing. The slope is positive means the curve is increasing. And f prime negative means that the curve is decreasing, the slope is negative. Coming from the left, if it's increasing and then it's decreasing, that creates a relative max. But now take a look at the point on the right, the other critical point we had over here. From the left, it's decreasing, and then on the right of that, it is increasing. So if the curve is decreasing and then increasing, that creates a relative minimum. So in this case, increasing again, f prime positive. So as we're looking at this, if we see that the derivative is positive and then the derivative is negative, that means the curve is increasing and then decreasing, creates a relative max. If we see that f prime is negative and then f prime is positive, that means the curve is decreasing and then increasing, and that creates a relative minimum. Speaking of increasing and decreasing, definitions for increasing and decreasing. It's increasing if the derivative of x is greater than 0, if the slope is positive, greater than 0, positive, on an interval. Right, increasing can only occur on a particular interval, not at a particular point. At a point, you're neither increasing nor decreasing. You're only increasing or decreasing or constant on an interval. Decreasing if the derivative is less than 0. Think slope, right? Derivative is slope. If the slope is less than 0, if the slope is negative, that means decreasing. And increasing, derivative greater than 0. That means slope greater than 0. Slope positive, that means increasing. All right, so when we write f prime of x greater than 0, you might be thinking that means slope is positive. And when we write f prime of x is less than 0, you might be thinking, okay, that is when the slope is negative. Okay, what about when the slope is constant? When the curve is constant. The curve is constant when the derivative of x is equal to 0 on an interval. And you might be thinking, well, is that the same thing as a critical point? Is a critical value? Not really. So the derivative, if you look at a curve like this, is equal to 0 at this point. F prime is equal to 0. It's equal to 0 at this one point, right? You get a little tangent line that's a horizontal tangent line. F prime is equal to 0 at this point. That's not constant. That is just a critical point. Constant would be on an interval. Constant would be you have a curve that for some reason flattens out like that. On this portion of the curve is constant. On that entire portion, the derivative is equal to 0 on the interval. Right? That's the difference between constant and a critical value. All right. I said this earlier. Same idea. Note that a curve often changes from increasing to decreasing or decreasing to increasing at critical values, but not always. Honestly, that's saying the exact same thing I said up here when I said that local extrema are critical values, but not all critical values are local extrema. We can explain this by the picture. The curve sometimes goes from increasing to decreasing, right? And if that happens, if you go from increasing to decreasing, we end up with a relative max. If we go from decreasing to increasing, we end up with a relative min. But sometimes that doesn't happen. Sometimes in this curve, like the one on the right here, we go from increasing to increasing. Right, on both sides of this curve, the graph is increasing and then it's increasing. Because it's increasing and increasing on both sides, we get no relative extrema. Increasing to decreasing, relative max. Decreasing to increasing, relative min. Increasing to increasing, not a relative extrema. Or decreasing to decreasing, not a relative extrema. All right, so the statement there is, note that a curve often changes from increasing to decreasing. That would be a relative max. Increasing to decreasing, that's relative max. Or decreasing to increasing would be relative min, but not always. And then if it's like increasing to increasing, then we get no relative extrema. Or decreasing to decreasing. In both of those cases, no relative extrema. Okay, let's go ahead and, although I've described it several times now, let's go ahead and officially define our local or relative extrema. A local or relative extrema, point C f of c, so the x value of c, the y value f of c, is a local max if f of c is greater than or equal to f of x for all x in the neighborhood of c. Point C f of c is a local max if f of c is greater than or equal to f of x for all x in the neighborhood of c. What we're saying is the y value at c f of c is higher than the y value of all the other surrounding points in a neighborhood of C. Right, so if you kind of think about it like this, here's a curve, here's C, that makes this point C f of C. The y value, or the function value f of c, is greater than all the other y values. It's greater than this y value and this y value. It's greater than all these y values. It's greater than or equal to all those y values in the neighborhood of C. How big is the neighborhood? Well, we get to kind of define how big our own neighborhood is, and so within a particular neighborhood, that's the highest point. That's what it means to be a relative extrema. It does not mean that it's the highest point on the entire curve. Okay, so this curve may then come over here and go up again and then back down again. This CF of C is still the highest point in its neighborhood. That makes it the relative extrema. All right, local min. Point CF of C is a local minimum, a relative minimum, if f of C is less than or equal to f of x for all x in the neighborhood of C. Same idea here, although now it's the lowest point as opposed to the highest point. Okay, and last definitions here, absolute extrema. Okay, so relative extrema means are in its neighborhood. What happens around it? The absolute is for the entire curve on the domain of the function. So an absolute extrema is point CF of C is an absolute max if f of C is greater than or equal to f of x for all x in the domain of f. So if we go back up to that picture that I had, this CF of C that we had here, this CF of C, trying to make that a better C and I failed. This CF of C is a relative or local maximum, but it is not the highest point on the entire curve, right? From what I can tell, if let's say our curve stops here, let's say our curve stops here, the highest point of the entire curve is over here. Now that point in orange happens to be both a relative max, because around its neighborhood it is the highest point, but also happens to be an absolute max. It is the highest point, right? The highest, the greatest y value, the greatest function value for all x on the domain of the function, wherever the function exists. Okay, that would be an absolute max. So, once again, an absolute max, point CF of C is an absolute max if f of C is greater than or equal to f of x for all x in the domain of f. Point CF of C is an absolute minimum, or min, if f of C is less than or equal to f of x for all x in the domain of f. Absolute max and absolute min. In order to find the absolute extrema, what we see happen is this. Let's say our curve is bounded here. It's bounded here, and it kind of maybe does this, and it maybe looks like this, okay? You have to look for two things. Your absolute extrema will come from two places. The first place your absolute extrema will come from are the relative extrema. There's two relative extrema. Those might be absolute extrema. The other two places, the other place that your absolute extrema will come from will be the endpoints. You got an endpoint over here, and we have an endpoint over here. So in order to find the absolute extrema, you first find all the relative extrema. And then you take the endpoints in the relative extrema, you plug those values into the function value, and you see which one has the highest function value, which one has the most lowest function value. So to find absolute extrema, you check your local extrema, you check your endpoints. Which x value has the greatest and least y value? Greatest becomes your absolute max, least becomes your absolute minimum. So check local extrema and check the endpoints. All right, that was a lot of definitions. What I want to do next is take the next video and do an example finding all the things that we talked about in this video.